The Virtuoso System Design Platform gives you the opportunity to accommodate pin swapping in the context of your physical implementation. We currently have our module level schematic that has 3 ICs and an I/O component on the bottom, LGA1. The module is placed but not routed. So to start, we'll run LVS to verify that our current schematic logically matches our physical implementation. To run LVS, we'll select SDP, Allegro Implementation, Layout versus Schematic from the VSDP text menu. We'll be running against our current physical implementation, which is a placed module that hasn't been routed yet. And when we select the OK button, LVS is run, and as we can see in the summary report, there's no issues found in the logical differencing, meaning that the logic in our schematic exactly matches the logic in the board. We also notice that we have some physical nets that are not currently routed. This is simply because we haven't routed our design yet. Right now we only have a placed module, which is typically when you would do most of your pin swapping. So now that we know we have no logical differences, we'll close our Design Differences window and we'll look at our physical implementation. We'll select SDP, Allegro Implementation, Launch SIP Layout from the VSDP text menu, and we'll select our Placement.SIP Design. In SIP Layout, we see our placed unrouted module design. SIP Layout can graphically show us which pins need to be connected together using what it calls rat's nest lines, lines of logical connectivity. So if we were to select Display, Show Rat's Lines by Net, I can select the I/O pins on the bottom of my package and see which nets each I/O pin is assigned to from the schematic. Based on our rat's nest lines, we can see that we can easily optimize some of the I/O connections on our module, and this can be done either manually or interactively. To interactively optimize our I/O connections, we can use the Place, Swap, Pins command. And this command will allow us to select pins on our I/O component. For instance, we'll select pin 1, which is currently connected to a net that runs over to the right side of the module. The pins that we can swap with are all highlighted in the user interface, and we can select the pin that we would like to swap with. We'll select a second I/O pin for swapping, and we can see that our rat's nest lines are swapped for us. And we can continue to select pins for swapping to try to reduce the amount of crossing of the rat's nest line. Similarly, SIP Layout provides automatic swapping to optimize our I/O connections. Let's reopen our design, go back to the original I/O connections that were inherited from the schematic, and again display the rat's nest lines for the I/O components on the bottom of the package. To accommodate an optimization of our I/O assignments, we can select Place, Auto Swap, and select to have our whole design auto swapped. When we select Place, Auto Swap, Parameters, the parameters form open. The automatic swapping allows you to set up to 10 swapping passes, the default being 2 passes with a maximum time of 60 minutes each. When we select the swap button in the auto swap form, we'll see the rat's nest be optimized for our I/O component to give us a much shorter crossing count for our rat's nest lines. We can see the swapping that was done by selecting File, View Log from the SIP Layout text menu, and the log file will indicate the swapping that was done in each of the swap passes. And we can see that pins on our LGA1 component have been swapped to try to reduce the amount of crossing count and reduce the total Manhattan length of the connections in the design. If we scroll down to the bottom of the log file, we can see that the starting Manhattan length was 135,000, and because of the optimization that was done, it was reduced to 123,000, a reduction of about 9.3%. We can save our design, and it's extremely important to note that our schematic and our physical implementation are no longer in sync. We've swapped pins in our physical implementation, and we no longer match our schematic. This will be caught in LVS. If we select SDP, Allegro implementation, layout versus schematic from our VSDP module schematic, we can rerun our LVS on our placement.zip. And LVS will clearly indicate that we have issues found in logical differencing. The pin swapping window will clearly indicate which pins have been swapped, and these pins on the schematic no longer match the layout on the board. And we can now go back and swap the pins on our schematic as well to make our schematic and our physical implementation match again. It is important to note that not all pins in SIP layout are swappable. Pin swapping is controlled by the library information, and more specifically, the chips view of a part, which is the logical to physical pin mapping, also controls whether or not pins are allowed to be swapped in the physical implementation. If we go find our LGA component in the library, we'll find that it's this chips view that is allowing SIP layout to accommodate the pin swapping. If we open the chips view in an ASCII text editor, we find the logical to physical pin mapping for our LGA component, and we'll notice that each of the physical pin definitions for pin 9, 8, 7, 6, and on down the line all have the same value for their pin group attribute. It's these pins sharing the same value for their pin group attribute that allows SIP layout to swap those pins in the physical implementation. So, the Virtual System Design Platform allows you to accommodate both manual and automatic pin swapping to optimize the I/O of your module. And it is very important to run LVS at some point to verify that your schematic and your physical layout share the same logic after doing any pin swapping or gate swapping.